This lesson is an add-on to our lesson about stoichiometry. It's still stoichiometry problems, but it's a little more real world in that you are going to be working problems where you're given a specific amount of two reactants rather than just a specific amount of one of the reactants and this excess unlimited amount of the other reactant. And if you'll read this top section, it says limiting reactant problems are when a specific amount of two reactants are present. So one of those reactants is going to run out first. The one that runs out first is called your limiting reactant because it limits how much can be made. Once a reactant runs out, the reaction stops. So that limiting reactant determines how much product can actually be created from a certain reaction. You'll know these problems because they're going to look like a regular stoichiometry problem, except in the problem itself you're going to be given two masses, and both of those masses are going to be of reactants in your reaction. And then it's going to ask you to find out how much product is actually created. So that'll be your clue to knowing that it's a limiting reactant problem. You're really going to work these problems exactly the same way that we've worked our other stoichiometry problems, but you're going to have to work two stoichiometry problems, one for each reactant involved. You're going to know the final answer. In other words, you'll know how much product is actually created by looking at the answers to the two stoichiometry problems you solved and choosing the answer that creates the least amount of product. What that means is that the reactant that's your limiting reactant, when it runs out, it's going to make whatever amount of product it can, and then the reaction stops. And since it's the limiting reactant, it runs out first, so it'll make the lesser amount of product. Okay, so let's kind of take a look at one of these problems and see how they look different from the regular stoichiometry problems that we've solved. Okay, in the example problem, we have aluminum chloride. It says it's an inexpensive reagent. Reagent is just another word for reactant used in many industrial processes. It's made by treating scrap aluminum with chlorine. If you start with 27, and that should just say grams, not go, 27 grams of aluminum and 4.05 grams of chlorine, which reagent is limiting? So that's the first part of the question. And then I'm going to explain how to work a second pretty common question that's asked with limiting reactant problems. And that second question is how many grams of the excess reagent will remain when the reaction's completed? In other words, the reactant that is your excess reactant will have some left over because it's in excess. And there's a way to solve how much of that's going to be left over when the reaction's done. For this type of problem, just like every stoichiometry problem we've worked, the very first thing you have to do is write and balance the equation. You have to have your recipe for the reaction to start. So we are doing a synthesis reaction where you take aluminum and chlorine, which is diatomic, and it's going to create aluminum chloride. Don't forget to write your formulas correctly. Aluminum has a +3 charge, chloride has a -3 charge. So when I crisscross those charges, that's where that 3 subscript comes from chlorine. Okay, everything's written correctly in the in the equation, and now I have to balance the equation because that's a pretty important part of the stoichiometry process. So I'm going to put a 3 here and a 2 here. That gives me 2 aluminums. So I need 2 aluminums on the other side. So I've got my coefficients, which remember represent our mole ratios of everything in the reaction, and I am going to start solving this problem. Now, I have 2 reactant amounts to start with. I have 2.70 grams of aluminum. Okay, I also have 4.05 grams of chlorine. So I'm actually going to set up 2 stoichiometry problems at the same time. And my goal is to figure out which one of these 2 creates the least amount of product, the aluminum chloride. Whichever one creates the least amount is my limiting reactant. So that's going to answer the first question. So remember, the very first step of a stoichiometry problem, once you have your written and balanced equation, is you have to get whatever units that are given to you in the problem, you have to get them converted into moles. So since I'm starting with grams of both, I'm going to use molar mass to help me get from grams to moles. 1 mole of aluminum weighs 27 grams, and you can look on the periodic table to see that. 1 mole of chlorine gas weighs about 71 grams. Okay, so now I have the units that I need to actually work with those coefficients for my balanced equation, because I have moles of each one of my reactants. Now I want to set up mole-to-mole ratios showing the relationship between what's given to me in each problem and what I'm trying to find. So for the top problem, I'm looking for the relationship between aluminum and aluminum chloride. Well, the number in front of aluminum is 2, so I'm going to put 2 moles of aluminum. And 2 moles of aluminum create 2 moles of aluminum chloride. Now, if you wanted to just say 1-to-1 at that point, totally fine. You're going to get the same answer. Okay, I want to set up a ratio in my second problem as well. I'm going to say that 3 moles of chlorine create 2 moles of aluminum chloride. Okay, and that takes care of my mole-to-mole ratios. These units are going to cancel out, which leaves my final step. And my final step for both of these should look really the same. I'm going to convert them back to grams of my product. So 1 mole of aluminum chloride, I'm going to put that on the bottom. And I'm going to look up the molar mass for aluminum chloride, so I'm going to add the mass of 1 aluminum and 3 chlorines. And that gives me 134 grams. Okay. And that'll be the same for both problems. 134 grams of aluminum chloride. Alright, that cancels out my moles of aluminum chloride, and I'm ready to actually solve this problem. Okay, when I put the math into my calculator and solve for these 2 problems, I find out that the aluminum can create 13.4 grams of aluminum chloride, and the chlorine can only create 5.10 grams of aluminum chloride. Since chlorine produces the lesser amount of product, we call chlorine our limiting reagent. Okay, and if this question happened to ask how much product is actually made in this particular reaction, we would say 5.10 grams, because that's how much can be made before the chlorine runs out. The aluminum is called our excess reagent. Okay, so because it's going to have some left over, we call it our excess reagent. So that brings us to the third part of this problem. The third part of this the second part of the problem says how many grams of excess reagent will remain when the reaction is completed. Now we know that aluminum is the excess reagent, but this involves an extra step that does involve an extra stoichiometry problem. So let's look at setting up that extra step for this particular problem. Okay, I went ahead and erased the problem that involved aluminum and finding out the amount of product made by aluminum because it's my excess reagent. And what I'm going to work is a third stoichiometry problem to show how much of that excess reagent is left over. And what I'm going to need is really the information from this particular stoichiometry problem. Alright, so since I know that every bit of this chlorine was used up in the reaction because it is the limiting reactant, it ran out, I'm going to set up a third stoichiometry problem where I find out how much aluminum was actually consumed in this reaction. So I'm going to take this limiting reactant amount, chlorine, 4.05 grams, and I am going to do a third stoichiometry problem where I see how much aluminum was used with that amount of chlorine. So 1 mole of chlorine weighs 71 grams because it's diatomic. Okay, and then I'm going to do a mole-to-mole ratio between chlorine and aluminum. So 3 moles of chlorine needs 2 moles of aluminum in this reaction. Okay, and then finally 1 mole of aluminum weighs 27 grams. That's going to tell me how many grams of aluminum were actually used in this particular reaction that reacted with this 4.05 grams of chlorine. When I do the calculation for this, I get 1.03 grams of aluminum used. That's not what this question's asking. The question's asking how much of this excess reactant, aluminum, is going to be left over when the reaction is done. Well, I just solved to find out how much was used up. There is one more step you have to do, and it is subtraction. So you're going to take the amount of aluminum that you started with in the reaction, which is 2.70 grams, and you're going to subtract the amount that you used up, which is 1.03 grams. So I'm going to do a simple little so 2.70 grams minus 1.03 grams, and that gives me 1.67 grams of aluminum that remains when this reaction is complete. So that is actually the answer to the second part of the question, this part, 1.67 grams. That's how much is left over when the reaction is complete. Now, that's a pretty involved process for that last part where we solved for how much of the excess reactant remains. There are a couple of different ways to actually solve that type of problem. I showed you one of the ways. Another way would be to take the amount of aluminum chloride that you know was produced, which was 5.10 grams. We found out that that's the amount that was actually made from our limiting reactant. And you could set up this third stoichiometry problem where you put in 5.10 grams of aluminum chloride, and you do a stoichiometry problem where you see how much aluminum it would take to make that amount of aluminum chloride. What you'll find out is that you're going to get this same answer, 1.03 grams, which you would then take and still subtract from 2.70 grams of aluminum. So you'll end up getting the same answer either way. So it takes a little practice, but you'll get used to doing that third step that's involved. Okay, the final thing we want to talk about, and it is because it's in your lab that we'll be doing next class, which is the decomposition of baking soda. So we're going to do that lab next class, and one of the things that you'll have to do in that lab is figure out the percent yield. Percent yield is kind of like giving yourself a grade for collecting a product. You want the number to be higher, just like in a perfect world, we want to make 100% on something. We want 100. In percent yield, the closer we get to getting 100% of the product that we could possibly have gotten, the better our percent yield is. So the way you calculate percent yield is you have to have two values. You have to have what's called theoretical yield. Theoretical yield is a perfect world value or an ideal value that you get from solving a stoichiometry problem. You shouldn't really ever get this value. This is like ideal perfect world. You know, if none of our equipment failed and there was no human error involved, we would get this particular value of product created. Actual yield is the value that we get that we've measured in the lab. So we go and we run an experiment, we collect a product, and we put it on a balance and mass it. That is called actual yield, what our lab gave us, what we were actually able to collect in the lab. So once you have these two values, theoretical yield and actual yield, you can set up a problem for percent yield. You take your lab value and you divide it by this perfect world value times 100%, and that gives you your percent yield. So it's a pretty simple formula. The toughest part of this is making sure that you set up a stoichiometry problem to get your ideal value, your theoretical yield, and that you're able to, in the problem, pick out the actual yield, the value that the lab generated. So let's look at an example problem of that. So this problem says that Professor H.C. Brown at Purdue University received the Nobel Prize in Chemistry in 1979 for his work on the chemistry of diborane, B2H6. This gas can be prepared by the following reaction. So it's giving us the balanced equation to start with. We don't have to worry about that part. And it's telling us that if we begin with 18.9 grams of NaBH4, so we have this reactant. We have plenty of this reactant, so I'm not going to worry about this being a limiting reactant problem because it's only giving me the mass of one of the reactants. And it's telling me that I actually could collect from the lab 7.50 grams. So I did my lab, I massed the amount of gas produced, and I was able to collect 7.50 grams. And then it's asking me to find the percent yield. Well, I have my actual yield, 7.50 grams. What I don't have is that theoretical yield to divide it by and then multiply it by 100%. The theoretical yield is the part I have to figure out. I know that I'm starting with 18.9 grams of my reactant, NaBH4. Okay, I want to see how much of this gas, diborane gas, I could make in an ideal world, in an ideal situation. So, before I can use my balanced equation, I have to convert grams to moles. So 1 mole of NaBH4. The mass is 38 grams, taken from the periodic table. That's the mass of 1 sodium, 1 boron, and 4 hydrogens. Okay, the ratio of NaBH4 to B2H6, the diborane, is 3:2. So 3 moles of NaBH4 can make 2 moles of B2H6. And then finally, I'm going to see how many grams of B2H6 I could make in an ideal world. So 1 mole of B2H6 weighs 28 grams. And now I can solve and see what mass I should get in an ideal situation. Okay, what I find out is that I can actually make, in an ideal world, 9.28 grams of this product, B2H6. So, this is my theoretical yield. Okay, my actual yield was given to me in the problem. So now I just have to do that last step of putting it into a percent yield calculation. So I'm going to take 7.50 grams, and I'm going to divide that by this theoretical perfect world value, 9.28 grams, times 100%. Okay, and that is going to give me my percent yield value. I want to be as close to 100% as possible, but I know that there's always human error in these kinds of experiments. And so I know I'm not going to get 100%. And in this case, I got 81% yield. And actually that's a good percent yield considering that the product you're collecting is a gas. Gases are probably pretty tough to collect just because they're state of matter, and then also to get an accurate mass without any of it escaping before you get a true mass value. So 81% yield is actually a good percent yield for that particular type of experiment. So once again, gave us the actual yield in the problem. We used the stoichiometry to solve and figure out what theoretical yield should be, ideal value, and then we took and put it into that percent yield calculation where we did the actual yield over theoretical yield times 100%. And that gave us the 81% yield.